Okay, so today we'll be talking about radian measure, area, perimeter, and arc length, all generally in relation to a circle. So typically so far we've usually looked at degrees for angle measurements. So, in a full circle, there's 360 degrees. However, that's a pretty arbitrary unit because we kind of just made it up. I guess it's just maybe a nice indivisible number, but it's not really based on anything. You know what I mean? So instead in math, sometimes we use what's called a radian measure. A radian measure is sort of based on a circle. So let's look at the circle and see how radian measure applies. So say we have a circle. This is the radius. Say it forms a sector with an arc length of r. Oh, that's pretty bad. Arc length of r. So it looks like this, right? The angle that's subtended or formed here, let's call it theta, is 1 radian. So 1 radian is equal to the angle subtended by a sector with arc length of r. So this has implications since we know that in a full circle there are 2 pi, the perimeter of a circle is 2 pi r. So if each r is a radian, that means in a full circle, so in 360 degrees, we have 2 pi radians. And that's a really useful piece of information because it can help us convert between radians and degrees. So let me rewrite that. So 360 degrees is equal to 2 pi radians. So from there we can say that 180 degrees is equal to pi radians. This is a very useful sort of conversion factor you can look at to help convert between degrees to radians and radians to degrees. So say we have 60 degrees and we want to convert that to radians. Well, we can just write out 180 degrees equals pi radians. 180 divided by what would equal 60? Divide by 3. So 60 degrees is equal to pi divided by 3 radians. We call this pi by 3. You can also go the other way around, of course. You can do, say you want to convert 1.7 radians to degrees. Let's write that pi radians is equal to 180 degrees. And we want to turn this pi into 1.7, right? So we can sort of multiply by 1.7 over pi. Of course, we have to do the same on the other side, so and then that gets us 1.7 radians is equal to this many degrees. And that's not going to be a nice number, so I'll leave it at that. If you've noticed here, I haven't really put any units for radians here. That's kind of on purpose. So although I usually do write radians with rad to indicate radians, radians is ultimately a unitless measurement because it's a ratio between lengths. So radians is defined as, so theta in radians, it's defined as arc length over radius. So remember, when the arc length was radius, r divided by r would equal to 1, and our radian measure is 1. But you see, these two are both lengths. So say they both have units of like centimeter. They would cancel out, making radians a unitless measure. But sometimes you might just add an r or a rad behind a radian measure just to make sure it's clear. Now we can transfer this knowledge to perimeters and areas and solving different features of a circle. So let's just review a few few things. So theta in radians is equal to arc length over r. That's very important. Remember that the area of a circle is equal to pi r squared. Remember the perimeter of a circle is 2 pi r. And let's remember how to calculate sectors. So sectors like this. Let's call this r. Let's call this arc length. Let's call this theta. To find the area of a sector, you just alter the area formula we know. So this sector is a fraction of the circle's total area, correct? So say, for now, let's say theta is in degrees. We're operating in degrees here. Forget radians for a second. The area of the sector would equal to theta over 360, right? Degrees. That's the fraction that the sort of slice takes up of the total circle. And then we can just multiply that by the formula for the area. And that's sort of by formula for a sector. So if you're looking at the whole circle, theta would be 360, that's 1, and you just get the original formula. But let's say we're talking in radians now. You can do the same thing. Theta is in radians, but this time, this will be 2 pi, because that's the total amount of radians in a circle, multiplied by pi r squared. Now notice that we can cancel things out, namely the pi. So area is simplified to 1/2 of theta r squared. That's important to remember. So let's try our hands on problems. And remember that none of these will be to scale. My art skills aren't quite there yet. So we have a circle here. We have arc length of A. We have angle in radians. It's pi by 3. And let's say this radius is 3 centimeters. And we want to solve for A. Well, let's remember that theta is equal to arc length over r. Remember, when we use this, it has to be in radians. This only works if it's in radians. If it's in degrees, if your angle is in degrees, none of this is going to apply. So we can just rearrange to solve for arc length. It's theta r, which is pi by 3 times 3 centimeters. So arc length is equal to pi centimeters. Pretty straightforward. And then the same thing can be done again, but this time they give you the arc length and they don't give you degrees, or I mean the measurement in radians, or they give you the arc length and they give you the radian measure, but they don't give you the radius. So you have any two of these pieces of information, you can solve for the other. Just a whole bunch of different rearrangements. Now let's look at a bit more interesting one. Say we get a sector here. This is pi by 3 again. And we get that this is 3 centimeters again. But now let's solve for the arc length of this side. Okay? So let's use the same formula. Arc length is equal to theta r. But realize that we're given the angle of this smaller sector, and we want to find the larger sector. We want to use this angle in our formula. So what is that equal to? Well, in a full circle, there's a total of 2 pi radians. So this angle would just be equal to 2 pi radians subtract pi by 3 radians. So let's put that in. 2 pi radians subtract by, take away pi by 3. Multiply the radius again, 3 centimeters. That arc length comes out to be 5 pi centimeters. So it's always helpful to sort of draw things out, to visualize things, if you've been given a mess of information. Now let's try an area problem. So we have another circle. Well, that's not a very good circle. Oh well. another angle here. Let's say it's pi by 6 this time. Let's say that the radius is 12 centimeters. So what's the area equal to? Well, area is equal to 1/2 radian measure r squared. So if we want to find the area of this sector here, what we have to do is sub in the values. So let's put in 1/2 times pi by 6 times 12 centimeters squared. And that area comes out to 12 pi centimeters squared. So that's the area for this sector here. But what about for this sector? Let me try a different color. This sector here. Well, you can use a similar principle to what we did before. So let's write the formula out again. Equals half theta times r squared. So here, again, it's the idea of that this full circle is 2 pi radians. So to find sort of this angle here, you can just do 2 pi radians, subtract pi by 6 radians. And it's the same radius. And that will evaluate to the area of this red section here. But I'm not going to go through it. Now for the perimeter, we can also look at that. So the perimeter will equal, well, for a sector, will equal the arc length plus 2 radii. So that's just, of course, referring to the arc length here and the 2 radii here. So we weren't given the arc length, but know that we have the radian measure and the radius, so we can find the arc length. So perimeter is equal to, remember, theta equals arc length over r. So therefore arc length equals theta r. So perimeter is equal to theta r plus 2r. So now we can just plug and check our values. That is pi by 6 times 12 centimeters plus 2 times 12 centimeters. And I'm not sure what that comes out to, but that will give you the perimeter of that sector. Now, as you've seen from this, these are just a few simple examples. There are many, many ways of sort of presenting the information. So always remember your formulas and remember what you're solving for, and try and draw a picture if you can. Add some labels, draw some diagrams, just to help yourself organize everything, since the formulas themselves are simple. It's just the process of understanding which formula to apply and what you're solving for that can make it more confusing.